Hello all. You might have already seen the previous two videos of ray optics. Now we are going to start with the refraction at spherical surfaces. Okay, so you can see this we are going to start a topic, refraction from rarer to denser medium at convex spherical refracting surface. So this you can see this is a surface which is convex XPY, and this is convex spherical refracting surface. And then it is rarer medium, denser medium, rarer medium with refractive index mu1, denser medium with refractive index mu2. So we are going to first draw the normal to this surface. And this normal will intersect this principal axis at point that is nothing but C, center of curvature. P, that you know, is the pole of this center point of this surface. C is the center of curvature. And NC, that we have drawn the normal to this surface. Now we are going to consider, so there are many actually cases we are going to see, from denser to rarer, then convex, concave, all these cases are there. But once you understand that what points you have to do, like first is you have to draw the surface, a principal axis, show the pole, then you draw a normal. Normal will intersect the principal axis at point C. Now let us say that this is a point object O. A ray will go from O to this point. Let us name this point as A. After it touches this surface, it won't go straight because there is change in the medium. There will be bending. So it will bend towards the normal as it is rarer to denser. One more ray we are going to consider, which is going to travel along OP, which is going to go straight, that will intersect this ray at a point which is nothing but the intersecting of these two rays will give us the image I. Now once you have shown the object, we have considered two rays coming from the object. After refraction they are intersecting at point I. That's the I is the image of the point object O. Now we are going to mark some angles. See, this incident ray makes an angle I, angle of incidence with the normal. Now it is refracted. So this is angle R, angle of refraction. Then we are going to mark other angles. This is angle of incidence and angle of refraction. R, angle of refraction. So this, you know, it is always between the ray and the normal. Now this object ray, the ray which is going from the object OA, makes an angle with the principal axis which is alpha. This refracted ray makes an angle beta, and this is angle which the normal makes with the principal axis, that is gamma. So we have three angles, alpha, beta, gamma. Angle made by the incident ray, then the refracted ray, and the normal with the principal axis. Once I show this, now we are going to drop a perpendicular from the point A to the principal axis. We will name this point as M. So we have now drawn the entire ray diagram of refraction from rarer to denser medium at convex spherical refracting surface. Now what is remaining is we have to derive now by using geometry. Derive a formula, and just we are going to use geometry with reference to this ray diagram. So AOM angle is alpha, AIM is beta, ACM, you can see the ray diagram, it is gamma. Now we are going to use exterior angle properties for two triangles. So first we are going to consider the triangle IAC. There we are going to use exterior angle property. So that will give you gamma is equal to r plus beta. From this we are going to get the expression for r, that is gamma minus beta. I mark this as equation 1. Then we are going to take the triangle OAC and again use exterior angle property. So in triangle OAC, if you use exterior angle property, I will be equals to alpha plus gamma. That is equation 2. Now you can see that we have got I and R. Now we are going to use the Snell's law. Sin I by sin R is equal to mu. So using Snell's law, sin I by sin R is equal to, you know that you might have seen the previous video and there we have talked about the Snell's law. So it is mu 2 1, that is refractive index of 2 with respect to 1. Now these angles are very small, so we can now consider the sin I approximately equal to I and sin R approximately equal to R, and also you know that mu 2 1 is mu 2 by mu 1. So please watch the video of the refractive index in which all these formulas, Snell's law are well explained. So now as angles I and R are small, sin I will be approximately equal to I and sin R will be approximately equal to R. When the angles are very small, the sin values and tan values are approximately equal to that angle. So we have I by R is equal to mu 2 by mu 1, then cross multiply. Now we had equation 1 and 2 where we got I and R, that we are going to substitute here. So mu 1 alpha plus gamma is I, and R we got it as gamma minus beta. Now one more thing that we are going to use here, that this alpha, again the angles are small, so we can consider alpha, gamma or beta as tan alpha, tan beta and tan gamma, and we can consider the triangle and use the formula for tan, that is tan alpha. So alpha can be considered as tan alpha, and see this triangle OAM, these are all right angle triangles, that AMC, AMI. So where we get these angles AOM, so we'll find the tan alpha, tan beta, tan gamma, which are same as alpha, beta, gamma, and substitute here. So tan alpha, which is equal to alpha, is equal to opposite by adjacent AM by MO. Similarly, beta is equal to AM by MI, and gamma is equal to AM by MC. So now we have this alpha, beta, gamma. This is our equation 3. Equation 1 and 2 were I and R. Then we got, after Snell's law and simplifying that, we got this as equation 3. In this equation 3, we are going to substitute now alpha, beta and gamma. Now what you can do in this, I've just substituted alpha, beta, gamma, take AM common and cancel it out. So mu 1 so you can see that in this equation numerator, each term is having numerator AM, so we cancel it out and we have got this. Now again if you see the ray diagram, okay, P and M are very close, so we can again approx MO as PO, MC as PC and MI as PI. So as points M and P are close, MO is approximately PO, MC is approximately PC, and MI is approximately PI. Now if you see the ray diagram, PO, always this distances in whether it is mirror or lens refractive index, we measure it from the center. So PO, we don't say OP, because it follows the sign convention of nothing but positive x-axis will be, the distance will be positive, negative x-axis will be negative. So if you see PO distance in the ray diagram is this side, left side, so that is nothing but negative, and it is the object distance, as O is object. So PO will be minus U. PO is object distance, it is negative because it is to the left side. We consider the negative x-axis as the negative distances. So even PC, now center of curvature is to the right side of the pole. So right side distances are positive, and PC is nothing but a radius of curvature plus R. And if you see PI, I is the image find again to the right hand side. So it is positive plus V. So now we are going to substitute this MO, MC, PC as PO, PC, PI, and then directly this distances in the equation with the signs. So this MO is PO, PO is minus U, and this is plus R, and this is plus V. Now you just open the bracket. Now I'm just going to take this R terms to the one side. So mu1 by R, mu1 by minus U plus mu2 by V equals to mu2 by R minus mu1 by R. And here you can take 1 by R common, mu2 minus mu1. So this is the formula for refraction from rarer to denser having refractive indexes mu1 and mu2 respectively at a convex spherical refracting surface, which is mu1 by minus U plus mu2 by V equals to mu2 minus mu1 by R.